NASA's Kepler telescope has identified an odd star, or is it a star that is giving astronomers pause and raising questions about the possibility of an extraterrestrial civilization?
In 2022, astronomers found a strange radio signal coming every 22 minutes using the Murchison Wide Field Array, and when they checked past records, they saw this signal had been reaching Earth since at least 1988.
The star from our perspective on Earth, and that makes the star get slightly dimmer. And so Kepler is looking at 100,000 stars simultaneously.
Usually, these signals come from pulsars, stars that flashlight as they spin. But this time, it was way more stable than any pulsar they knew. What is really behind these weird noises that are terrifying the scientific community? Let us dive into the real truth behind these anomalies that could lead to the first encounter with alien life. Distant stars' unbelievable signals. The distant object known as GPM J183910, located about 18,000 light-years away from Earth, transmits signals to us in a rather inconsistent pattern. These signals, or pulses, can last anywhere from a brief 30 seconds to a longer 5 minutes, and they do not arrive at regular intervals. The gap between the pulses can vary by over 6 minutes, which makes it difficult to predict when the next pulse will come. Despite this irregularity, the object is believed to be a neutron star, a type of star known for its complex behavior, where multiple factors could be influencing how and when these pulses are sent to us. For over 3 decades, astronomers have been sifting through data to understand the behavior of this source. They have been able to track its rotation, finding that it spins around completely every 21 minutes and 58 seconds. What is surprising is that, contrary to what is typical for neutron stars, this rotation rate has not changed significantly over the years. Neutron stars usually lose energy as they emit radiation, which should slow down their rotation over time. However, GPM J183910 has shown remarkable consistency in its rotational period, with any possible decrease in speed being so minor, less than 0.28 milliseconds, that it's almost negligible. This consistency is unusual for a pulsar, especially one that rotates as slowly as GPM J183910. Pulsars are generally known for their reliability in timekeeping across the vast distances of space, acting like cosmic clocks due to their regular pulsing. Yet, the stability observed in GPM J183910 is unexpected for a slowly rotating pulsar, raising questions about the forces at play. This could indicate unique properties or conditions affecting this neutron star, which might challenge or expand our current understanding of pulsar physics. The ongoing analysis of this object's data might reveal more about its nature. Are we observing a rare phenomenon? Or are there unknown aspects of neutron stars that we have yet to discover? The consistent behavior of GPM J183910 in the face of expected energy loss is intriguing and suggests that there might be more to learn about the stability and energy dynamics of these celestial bodies. As researchers continue to monitor and study this object, they hope to uncover further details that could provide clearer insights into the mechanisms governing neutron stars and their emissions. To grasp why pulsars like GPM J183910 are intriguing, we must first understand what pulsars are and why they typically slow down over time. Pulsars are what remain after massive stars explode and die. These remnants, known as neutron stars, are among the densest objects in the universe, second only to black holes. To visualize their density, imagine compacting the mass of the entire human population, around 8 billion people, into a spoonful. Neutron stars are heavier than the sun, yet fit into an area as wide as Manhattan. These neutron stars generate incredibly powerful magnetic fields, the origins of which are still not fully understood by scientists. The connection between these magnetic fields and the signals or pulses we receive from pulsars is quite complex. It starts with an electron near the neutron star's magnetic poles. This electron gets accelerated by the strong magnetic field and releases a light particle known as a curvature photon, which follows the curved path of the magnetic field. This event begins what we detect as a pulse. The photon travels until it can no longer follow the curve of the magnetic field. At this point, it releases its energy into a field of what are called virtual particles, leading to the creation of an electron and its counterpart, a positron. These particles then quickly release energy in the form of other light particles called synchrotron photons. Now, let's discuss the unusual nature of GPM J183910's stability in rotation speed. Commonly, pulsars slow down because they emit energy over time, like a spinning top that eventually stops spinning. However, GPM J183910 has maintained a consistent rotation speed for over 35 years. This consistency is peculiar because it contradicts the typical behavior expected from pulsars, which should gradually lose energy and slow down. The fact that GPM J183910 does not show signs of slowing could suggest that our current understanding of these cosmic objects might be incomplete or incorrect. Perhaps there are factors or conditions affecting this particular pulsar that we have not yet discovered or understood. This situation provides a significant challenge to astrophysicists and requires a reevaluation of what we know about pulsar dynamics. Moreover, the steadfast behavior of GPM J183910 raises several questions about the mechanisms that regulate energy and rotation in neutron stars. Is this pulsar an exceptional case, or are there unknown processes at play that could explain its unusual stability? These questions highlight the need for continued observation and study of GPM J183910 and similar pulsars. Understanding why this pulsar defies the typical patterns observed in others could lead to breakthroughs in our knowledge of the universe and the fundamental laws that govern celestial phenomena. As we delve deeper into the study of such anomalies, we might uncover new aspects of physics that could reshape our understanding of the cosmos. In the vastness of space, each synchrotron photon has the potential to generate a new electron-positron pair when it hits a specific angle with the magnetic field lines. This event sets off a chain reaction. As more photons and pairs are created, they multiply rapidly. This process continues until the photons no longer have the energy to produce new pairs, at which point the cascade stops. The photons that result from this intense activity are then emitted into space, while the original electron keeps moving along the magnetic field lines, generating even more photons and continuing the cycle. The intensity of this entire operation is why we can detect the light from a pulsar, a small star remnant, from thousands of light years away. As we begin to understand GPM J183910, another part of the cosmic puzzle appears, showing us the unique dance of light and magnetic fields in space, mesmerizing light from spinning stars. Yet the light from a pulsar doesn't appear as a steady stream. Instead, we see it in bursts or pulses. This happens because the magnetic poles of a neutron star don't line up with its axis of rotation, similar to how Earth's magnetic north is different from its geographic north. Like a giant lighthouse in the sky, a pulsar sends beams of light sweeping across the universe as it spins. From our perspective on Earth, these beams pass by us repeatedly as the pulsar rotates, appearing as brief, recurring flashes. Detecting these flashes, however, requires a radio telescope due to the radio frequency of the light emitted. Moreover, the light from pulsars is polarized, meaning it aligns along a specific axis. This alignment is characteristic of neutron stars and is evident in the signals we receive, like the 22-minute signal that shows consistent polarization. Occasionally, this alignment shifts dramatically, with the axis of the light's polarization rotating 90 degrees to form a perpendicular line before returning to its original position. These abrupt changes are indicative of the dynamic processes at the pulsar's poles and highlight the complex interactions in space. Despite the strong evidence that attributes these signals to a pulsar, an unexpected factor complicates this interpretation: the slow rotation rate of the neutron star. The combination of its sluggish yet stable rotation is unusual and raises questions about our current understanding. While it might be tempting to quickly conclude that these observations confirm the presence of a pulsar, the slow rotation rate introduces a significant variable that suggests we may need to reevaluate our assumptions and continue our investigations into these distant cosmic phenomena. This situation calls for a more cautious approach in drawing conclusions from our observations, underscoring the need for further study and deeper analysis of these intriguing cosmic events. Let's take a clearer, more skeptical look at this phenomenon. Pulsars, often celebrated as powerful cosmic lighthouses, gradually lose their strength as they emit intense beams of light into space. According to the basic principles of energy conservation, as they radiate energy, they inevitably slow down. This deceleration continues to a point where these pulsars no longer have enough energy to maintain their pair production cascades, which are essential for their light emissions. They then enter what experts dubiously call Death Valley, a specific area on the graph where neutron stars are plotted based on their rotation speed and how quickly this speed decreases. In this so-called Death Valley, represented by a gray band, a pulsar's functionality supposedly ceases, and it should no longer emit light like the vibrant beacons they were once known to be. Intriguingly, our current signal under scrutiny falls well below this critical threshold in Death Valley, suggesting that, if it truly were a pulsar, it should be completely inactive. Yet astonishingly, we continue to receive signals from it. If we examine the typical behavior of known neutron stars on this graph, we observe that they usually spin at a rate of 10 times a second to once per second. However, the signal we are studying spins only once every 13-18 seconds, making it over 1,000 times slower than an average pulsar. This exceptionally slow spin rate would generally not be problematic if the star were also losing its spin rapidly. Such a rapid loss of spin would elevate its position on the graph, moving it out of Death Valley and indicating significant energy release capable of sustaining the light-producing pair production cascades. However, the star associated with our signal exhibits a perplexing level of stability in its rotation, which contradicts the expected behavior of a fading pulsar. This uncharacteristic stability challenges our understanding and raises questions about how we are still able to detect its signal when it should theoretically be silent. In light of these anomalies, the astronomers who discovered the signal have proposed an alternative explanation. They suggest that the star might not be a typical pulsar, but rather a magnetar, which is a type of neutron star with a magnetic field strength tens of thousands of times more potent than that of the weakest known neutron star fields. Magnetars are subject to what are known as starquakes, dramatic events where the intense magnetic pressures combined with the slowing of the star's rotation cause the star's crust to crack and shift. This scenario is akin to an overstretched rubber band finally snapping back to a less strained state. During such starquakes, the star's magnetic fields can abruptly realign, triggering the release of energy in the form of light that is detectable by our instruments on Earth. This speculative hypothesis serves to explain how a neutron star, seemingly too weak and slow to emit any light, could still be visible from Earth. It introduces the possibility of rare but significant cosmic events that allow a star to continue shining against the odds. While this explanation may stretch our current understanding of stellar behavior, it at least provides a potential solution to the puzzling stability and visibility of such an unusual star. This scenario encourages a more cautious and open-minded approach to interpreting unusual astronomical phenomena, reminding us that our universe often operates in ways that defy straightforward explanation and that our scientific models, though useful, are not infallible. While we look into the workings of neutron stars, we shift to other space oddities that might help explain the puzzle of GPM J183910, magnetar deadly theories and surprising signals. In 2004, the starquake from SGR 180620 released such a tremendous amount of energy that, had it occurred a mere 10 light-years from Earth, it could have potentially wiped out much of life on our planet. This incredible event prompts us to wonder if the peculiar 22-minute signal from GPM J183910 could be the result of a similar cosmic phenomenon. However, the idea of linking this ongoing signal to a magnetar, which is known for such explosive episodes, doesn't quite fit with what we know. To start, let's consider what we typically expect from starquakes. These events usually emit energy across various wavelengths, including X-rays. Yet, when astronomers examine the region from where GPM J183910 broadcasts, they find no X-ray emissions where there should be some. Moreover, the notion that a magnetar could continuously emit for more than 30 years contradicts what we understand about these phenomena. Starquakes are brief and intense. They don't just keep going for decades. This long-lasting signal baffles us because it seems to break the rules of how we expect these cosmic bodies to behave. Then, we have the ongoing theories proposed by astronomers. One such theory suggests that the source of this unusual signal could be a highly magnetic white dwarf. This type of star is what remains after a star has used up most of its nuclear fuel and did not have enough mass to compress further into a neutron star. If one of these white dwarfs had a particularly strong magnetic field, it might be able to produce the kind of radio signals we are detecting from GPM J183910. This theory, while interesting, is problematic because it requires a magnetic strength that has never before been observed in white dwarfs. The only white dwarf known to emit radio waves similar to a pulsar, AR-SCO, does so at levels far less intense than what we observe from our strange signal. As we delve deeper, the complexity increases. If the signal isn't coming from a standard neutron star or an unusually magnetic white dwarf, what could possibly be the source? Each hypothesis brings more questions than answers, showcasing the vastness of what we do not yet understand about the cosmos. This continuous signal doesn't just defy our current knowledge, it practically mocks it, presenting a challenge to every model we've constructed about stellar behavior and star deaths. This ongoing cosmic puzzle not only captivates us with its stubborn resistance to explanation, but also highlights the limits of our astronomical theories. It serves as a stark reminder of the universe's vast complexity and the many unknowns we have yet to uncover. While we strive to fit this anomaly into our existing frameworks, it might just be hinting at a new kind of celestial phenomenon entirely, one that could reshape our understanding of the universe. This exploration pushes the boundaries of our knowledge and calls us to think beyond the conventional, perhaps leading us to discover entirely new aspects of the cosmos. If a white dwarf isn't the answer, what other explanations might we consider? Observations have shown that interactions between stars and exoplanets, as well as two brown dwarfs orbiting each other, can produce low-frequency radio waves. However, these emissions are extremely weak, about 100 million times weaker than the signal from GPM J183910. It appears that none of our existing explanations can adequately account for this unusual 22-minute signal. While the absence of a clear explanation may be irritating, it's exactly these kinds of challenges that spark excitement among astrophysicists. Discovering data that contradicts what we previously believed can lead to major breakthroughs in our understanding of the universe. Our current understanding of neutron stars seems less certain with this new signal. The astronomers working on this are optimistic. The fact that they were able to detect this signal so clearly suggests that there might be more similar signals hidden in the vast amount of data we've already collected. Like GPM J183910, these signals could be waiting in our existing data, just waiting to be discovered. Finding more signals like this one could help us better understand the forces at work in regions beyond where neutron stars typically end their lives. Whatever is causing this 22-minute signal, it's likely to introduce us to completely new phenomena that we haven't encountered before. The excitement here isn't just about finding an answer, but about the path to uncover something new and completely unexpected. Exploring these unknowns is what drives scientists and expands our knowledge. By investigating these signals further, we might be able to unlock new insights into the behavior of celestial bodies and possibly even redefine some of our current theories about the universe. What could be causing this unusual signal? The answer might just reshape our understanding of space and introduce new concepts in astrophysics. This continuous search for understanding, driven by signals like the one from GPM J183910, shows how much we still have to learn about the cosmos. Every new piece of data, especially one that challenges our existing theories, provides a valuable opportunity for scientific advancement. It pushes us to question what we think we know and to explore possibilities that were previously considered improbable. This process is not just about satisfying scientific curiosity, it's about expanding the boundaries of human knowledge. The potential to discover something entirely new is what makes this pursuit so compelling and essential. What might the source of the 22-minute signal be? Whatever it turns out to be, it promises to be a fascinating addition to our cosmic knowledge. Moving from the steady neutron stars, we find many space questions that challenge what we know about the universe. Strange, fascinating stars and alien galaxies. Astronomy is more than just looking at stars and recording data. It involves continuous challenges that often mock our efforts to decode the universe. Consider Tabby's star, found by Tabitha Boyajian. This star dims by up to 22% at unpredictable times, confusing astronomers. Initially, it led to wild guesses, including theories about large alien structures. Now, the prevailing thought is that a massive cloud of dust might be causing the dimming. However, we still don't have a definite answer, keeping Tabby's star under constant observation. Another curious case is Przybylski's star, discovered by Antoni Przybylski in 1960. This star contains a mix of elements and radioactive substances that shouldn't be there according to the usual rules of nuclear decay. The explanations proposed include strange magnetic fields, or the star consuming a planet rich in these strange elements. Yet, no explanation has completely satisfied the scientific community, reminding us of our limited understanding of stars. Then there's NGC 1052 DF2, a galaxy that seems to ignore the common rules of the universe. It lacks almost all dark matter, which is thought to form a large part of the mass of most galaxies. This unusual characteristic has forced scientists to rethink their ideas about how dark matter is distributed across the universe. Hyperion, a moon of Saturn, also stands out because of its unusual appearance and behavior. Its surface looks like a sponge due to its many craters, and it releases a beam of static electricity into space. This unexpected behavior is just another example of how celestial bodies can behave in ways we don't yet fully understand. Rogue planets are another intriguing topic. These are planets that roam the galaxy without orbiting a star. Discovering such planets challenges our previous beliefs about how planets and auroras form, as these planets show auroras similar to those seen on Earth, despite having no star. Neutron stars are typically known for their powerful X-rays or radio waves. However, some have been observed emitting infrared light, suggesting they might be surrounded by dust disks. This finding is unexpected and adds to the complexity of our understanding of these dense stellar remnants. One of the most captivating events in the search for extraterrestrial life is the detection of the WOW signal. Jerry Amon discovered this strong radio signal in 1977, which lasted for 72 seconds and never repeated. This event led to numerous theories about its origin, including a possible alien signal because of its focused frequency and strength. However, despite many attempts, the signal has not been detected again, which keeps it a subject of intense research and speculation. The WOW signal initially led many to believe it might have come from an intelligent source due to its peculiar characteristics. However, a theory proposed by Antonio Paris in 2017 suggested it could have been emitted by comets passing through the area, as these comets emit hydrogen, which could produce a similar frequency. Even though this idea offers a possible explanation, the original intensity of the WOW signal was much stronger than what was observed from these comets, adding to the ongoing debate about its origins. Despite many efforts, including those by the Breakthrough Listen project to pinpoint the source of the WOW signal, no repeat signals have been found. This ongoing puzzle continues to intrigue scientists and the public alike, as it suggests there are still many unknowns about the universe. Certain observations during spacecraft flybys, such as those involving the Galileo and NEAR probes, have shown unexpected changes in speed when they passed close to Earth. These unexpected changes have puzzled scientists, leading them to consider the possibility of new laws of physics or other unknown elements that might influence the paths of these spacecraft. In the pursuit of understanding whether life exists beyond Earth, some galaxies have demonstrated unusual infrared light patterns. These patterns hint at either very intense star formation or, more intriguingly, the possibility of technologies from advanced civilizations. One galaxy, identified as WISE J22244361, shows such characteristics, but scientists need to do more study to clarify the source of these unusual emissions. Space is filled with phenomena that defy simple explanations. Among these are hypervelocity stars, which travel at speeds exceeding 1,000,000 miles per hour, far faster than typical stars. It is believed these stars are flung from their galaxies by strong gravitational forces, possibly from close encounters with a supermassive black hole. Black holes, particularly those of intermediate size, represent another area filled with unanswered questions. These black holes are theorized to fill the gap between smaller, stellar-sized black holes and the gigantic supermassive black holes found at the centers of galaxies. Proving they exist and understanding how they form continues to be a challenge for astronomers. Another peculiar space phenomenon is the Great Attractor, a point in space that exerts a powerful gravitational pull on galaxies, including our own Milky Way. This area draws these galaxies toward it at significant speeds. However, our view of the Great Attractor is blocked by our own galaxy, making it difficult to study and understand what it truly is or what it consists of. Fast radio bursts, or FRBs, are short-lived yet extremely powerful bursts of radio waves that have been detected since 2007. The source of these bursts remains a major question in astronomy. While some FRBs occur repeatedly, others appear only once, making it challenging to pinpoint their origins. Theories about what causes FRBs range from collisions between neutron stars to signals from highly advanced extraterrestrial technologies. Gamma-ray bursts are some of the most intense and brightest events we see in space. Scientists believe these bursts occur when very large stars collapse, or when neutron stars come together. Although these bursts release a lot of energy, scientists are still trying to fully understand how and why they happen. Each new gamma-ray burst observed gives astronomers important clues and helps them learn more about these powerful space phenomena. After seeing different space puzzles, we return to neutron stars with a better grasp of the forces in the cosmos. Hidden dark matter in space pulsars are another intriguing space anomaly. These are neutron stars that spin rapidly and emit beams of electromagnetic radiation, which we can detect on Earth. Some pulsars have episodes where their spin suddenly speeds up. These are called glitches. The reasons behind these glitches are still not clear. By studying these sudden changes, scientists hope to learn more about the inner workings of neutron stars, which are some of the densest objects in the universe. The Hubble Space Telescope has shown us incredible images, including what seems to be a huge crash between two clusters of galaxies known as the Bullet Cluster. This event has been crucial for studying dark matter, because the way these galaxies interact can't be explained just by what we can see. Instead, the gravitational effects suggest there is more dark matter that we can't see. Understanding dark matter is one of the most challenging tasks in physics today because it makes up most of the universe's mass, but remains invisible and undetectable by conventional means. Gravitational waves, which are disturbances in the fabric of space and time caused by some of the most violent and energetic processes in the universe, were directly detected for the first time in 2015. Albert Einstein first predicted these waves over a century ago, and now they offer a brand new way to observe the cosmos. By detecting waves from events like mergers of black holes or collisions of neutron stars, astronomers can explore phenomena that are otherwise invisible in electromagnetic observations, marking a revolutionary advance in our ability to study the universe. The study of exoplanets, planets outside our solar system, continues to surprise astronomers. For instance, some exoplanets, known as hot Jupiters, orbit extremely close to their stars. These planets have very high temperatures because of their proximity to their stars, which challenges our traditional ideas about how planets form and move around their stars. The existence of hot Jupiters suggests that planets can migrate significantly from where they initially form. Another exciting area of space exploration is the search for water on other planets and moons. Water is crucial for life as we know it, and finding it in space is a significant step toward discovering life elsewhere. Scientists have found signs of water beneath the surface of moons like Europa and Enceladus, and evidence of water in Mars's past. These findings have sparked intense interest in the possibility of life beyond Earth. The idea that other worlds in our solar system might host environments suitable for life, even if only microbial, expands our understanding of where life could exist and encourages ongoing exploration and study of these distant places. The exploration of the earliest stars, referred to as population 3 stars, seeks to shed light on the first group of stars born following the Big Bang. These initial stars are believed to have been incredibly large and to have lived for only a short period. Discovering remnants of these stars today could offer significant insights into the conditions of the early universe. Despite the potential wealth of information they hold, finding these stars is difficult because they are very rare and located at great distances from us. Cosmic voids represent another fascinating aspect of space. These are enormous areas within the universe where very few galaxies exist. Despite their emptiness, these voids are crucial for understanding the broader structure of the universe. By examining how these voids are spread out and their characteristics, astronomers can gather clues about the forces that have shaped the cosmos. Another key focus in astronomy is the investigation into dark energy, the strange force thought to be causing the universe to expand faster over time. Dark energy is believed to constitute about 70% of the total energy density of the universe. However, what exactly dark energy is remains elusive. Scientists use tools like the observation of distant exploding stars, supernovae, clusters of galaxies, and the cosmic microwave background to try to understand more about this hidden force. The concept of time is also a central topic of study. The phenomenon of time dilation, which is a prediction of Einstein's theory of relativity, has been proven through various experiments. Yet, the deeper nature of time and how it intertwines with space is still under thorough investigation by theorists. Astrobiology, the study of potential life beyond Earth, includes the search for signs of life on other planets and moons. The discovery of extremophiles on Earth, organisms that thrive in extremely harsh environments, has broadened our view of where life might exist elsewhere in the universe. Current missions to places like Mars, Europa, and Enceladus are not just about finding life. They are also looking for environments that might support life. Research into cosmic rays is another area packed with questions. Cosmic rays are high-energy particles that travel through space and come from sources such as exploded stars and active centers of galaxies. Understanding where these particles come from and how they interact with Earth's atmosphere is crucial for both basic physics and predicting space weather. The universe is continually presenting us with new and complex phenomena that challenge our current understanding. Every new discovery, be it peculiar stars, wandering planets, strange signals, or the underlying nature of dark matter and dark energy, pushes the limits of our knowledge further and prompts new questions for scientists to explore. As we develop more advanced technology, we gain deeper insights into these cosmic wonders, revealing layers of intricacy previously unseen. This ongoing quest not only demonstrates humanity's relentless curiosity, but also highlights the dynamic nature of scientific inquiry in our attempt to decode the vast and intricate universe. Each investigation, whether it leads to clear answers or more questions, is a step forward in our path to comprehend the cosmos in all its complexity. The perpetual cycle of discovery and understanding underscores the boundless potential of human intellect and the endless puzzles that await our exploration. Is this strange radio signal a natural phenomenon we haven't discovered yet? Or could it be a message from an intelligent source? What do you think is behind this 35-year-old anomaly? Share your thoughts in the comments, and don't forget to like and subscribe for more.